Okay, second half of Work and Energy 2, multiple choice section, numbers 13 to 24. Okay, so 13 brings into question, brings up a topic that, at least when I've been doing this in 2020, which is the first time when I made these screencasts, the one topic that I really haven't talked about too much, and that is an alternate way of looking at gravitational potential energy. And so, while it doesn't really stop you from doing the problem, there's a lot of things in here that are almost definitely going to confuse you. This is probably the biggest one, right here. This right here isn't really an official formula. This is just something they made up so that it would match with this. But this is what I'm talking about. When you look at this, and they say that the gravitational potential energy, hold on. And they say that we're used to gravitational potential energy being just simply mgh. The higher you go, the more energy you have. What's so freaking complicated? Well, the world is complicated, my friends, because their equation says that gravitational potential energy is negative, first of all, big G, the mass of the planet, the mass of the object whose energy you're considering, or that's actually part of the system, but the other object, because in this, what's inherent in the G, is the Earth. Right? So, divided by the distance. Okay. So, first, this works as long as you are really close to the surface of whatever planet you're talking about. I mean, our atmosphere in thickness compared to the Earth itself is the same as an eggshell is to an egg. It's not a huge part of it. In fact, if this is the Earth, that's probably the entire atmosphere, that thickness of that line. Everest would be, that. All right? So we think we're hot crap for climbing Everest, but really, compared to the size of the Earth, is nothing. And we also talk about, we'll dig a hole in the center of the Earth. Eggshell, right? You're going to the yolk? Good luck. Let alone the fact that it's molten stuff down there. But anyway, I digress. As long as you're in this little space right here, you're good. This works. This works. Because really, this right here doesn't vary. Well, the truth is, as you get farther from a planet, this goes down. So technically on Everest, G is actually, if they've measured, it is a little less than 9.8. 9.7 something probably. Point being, is this only really works as an approximation as long as you're really close to the surface of a planet. As soon as you step away and you consider the gravitational potential energy between, say, Earth and some satellite or the moon out here, we start to get distances that they start to reduce G considerably, and that's where this comes in. This is actually more universal. So what are the things at play here? G is the universal gravitational constant, 6.67 times 10 to the negative 11th? 19th, 11th, 19th, I can't remember now, I think it's 11th. Mass of the Earth, the mass of whatever object is in the system with it, and by the way, this could be any planet really, star, okay. This is the distance between, now this is important, the centers of the objects. So it includes the radius of each object. And in fact here, to make us really see that, we'll make this object a little larger, almost like a binary star system. All right, so it's measured between the centers of the objects. And here's what we notice, is that the truth is, as we get farther and farther away, this number gets smaller. But if you got far away and you let it go, the force on this wouldn't be, so if you were really far away, so this isn't to scale, but right, if you were really far away and they can still feel each other, this would not feel much of a force. Right? Gravitational force is big G, m1, m2, divided by the distance between them squared. you'd be pretty far away. You wouldn't feel much of a force. But let's say nothing else was happening, so you would start to slowly accelerate. And you would speed up a little bit, and speed up a little more, and speed up a little more. And as you got closer, the force would increase, so you'd speed up even faster, and you could slam into the object. So you do have a potential energy out there. And you have quite a bit of it, right? By the time you hit the Earth, you'd be moving. All right. So that's weird. The farther away I get, though, this number, ignoring the negative sign, that value gets smaller and smaller. Oh boy. So how do we account for this? Well, what we say is we put a negative in front of it. And now, for about the only time that I can think of in physics where negative isn't necessarily a direction, it's a is literally like an integer type number. Like it's a, so if you're here, the number's big, but it's negative, so you have, like, say, negative 100 GPE. So right here. Here, you might have negative 10. Well, negative 10 is technically more energy than negative 100. See, we describe it in terms of what's called an energy potential well. And the way you look at it is this. If you dug a well, a deep hole in the earth, and you called the ground 0, and the bottom of the well negative whatever, falling from 0 to negative whatever would give you a lot of kinetic energy and would still be a large change in potential energy. And so therefore, and the change is all that really matters. So where we set 0 is arbitrary. So where do we set 0 here? Where's the top of the hole? Here's what we do. We basically say it's very far away. The phrase is at infinity. In other words, this gets so big that this essentially goes to 0. No matter what this is, let's just say this is 50. I don't know what it is. You divide it by 17 trillion. Your calculator is going to be like, there's going to be so many zeros after the decimal point before you actually get to a digit. You might as well be like, just it's 0, whatever. So it's kind of an approaches kind of thing. So very far away is 0. And you would fall from that very far away to here. So, you could compare, if this was, for example, down here, if this was 100 million and this was 10, hell, just call it 0, right? What's the chance? What's $10 to 100 million, right? So, or if I called it a billion, 100 billion. Is that 100 million right there? That's 100 million, sorry. 100 billion. 10, really? Who cares, right? So, way far away can be considered starting at 0. All right. So, how much potential energy you have is really dependent on this, and that it comes out negative because we have to describe it in terms of a well. All right, all that's great. We can still use this when we're close to the Earth, and most of the problems you're going to run across are going to be close to the Earth. This, notice, the energy requires 2 objects. It's not so obvious with this that it's 2 objects. You think, oh, the object has a potential energy. It can't unless it's with a planet or a star or something. That's where this G comes in. So there really are still 2 objects here. It's you, right? Little old you, and the Earth, or whatever moon, or whatever object you're on. Okay, so there's that quick lesson. Now, for this one, I don't know if we need all that information, but it's, as a physics teacher, I need to run that past you. Non-rotating spherical planet with no atmosphere. Okay, it's interesting. With a mass m and a radius r. So here's our planet. And its center, because that's going to be important. Radius is r. Mass is m, big M, big M. A projectile of mass m is launched radially outward. So this would be a radius here. So we're going to launch our projectile this way. With an initial speed v, which is this mess. We'll come back to that. They only picked this. This is not an official formula. This is just, they picked a, quote, value that's going to, as you can tell, it has R's and M's and big G. It's going to match up nice. So, yeah, don't sweat that. But it has this initial speed. The potential energy of the projectile planet system as a function of the projectile's distance, r, little r, from the center of the planet, is given by. So, at any given location, as this thing flies away from the planet, then its potential energy is given by, this is little r, right here. This is the mass of the object that you launched, the little m. This is the mass of the planet. And of course, g is a constant. the greatest distance from the center of the planet that the projectile reaches is. So at some point, it is going to, gravity is going to keep pulling it back, so it's going to slow it down, and it's going to stop it, and it will start to fall back to the planet. All right? So where is this stopping point? Okay. So here's where the energy part comes in, and this is the part, given that, I would almost want you to pause it and see if you can figure out the conservation of energy here. When it's launched, it has an initial mechanical energy. When it stops, it has a final. So notice the approach here is that there's no air resistance, particularly in space, but there's no atmosphere on the planet, none of that. So the two should be the same. What form is it in when you launch it? Careful. Careful. I'm pointing at you. Be careful. Yes, it is in kinetic, but there is also some potential. Remember, this potential energy is measured to the center. So we do have some gravitational potential. At the end, it is all in the form of gravitational, because this is where it stops before it starts coming back down. Okay, so let's figure out what these are. Well, or expressions for them. I'm probably going to need to go, let's go to another piece of paper for this. So I know that my initial mechanical energy is my initial kinetic energy plus my initial gravitational potential. Kinetic energy is 1/2 the object has, so it's little m, and then v squared. Okay, this is v. We're going to square it, which is going to get rid of this square root. Cool? That's all it's going to do. So it's v squared comes out to be big G, big M, divided by 2r. What about the potential energy? Well, potential energy is this distance, which is big R, all right, is actually little r for this situation when at the start. So the potential energy is negative, capital G, capital M for the mass of the planet, mass of the projectile, divided by big R. So if you're like, well, wait, this has little r, it's because at this launch point, your distance from the center is the radius of the planet. Let's clean this up a little bit. So I got mechanical energy initial is equal to, let's see, put a 2, it's going to be a 4, so it's going to be big G, big M, little m, over 4r. This 2 here, make a 4, so r in the bottom, minus, alright, now this just has an r in the bottom, so let's take a moment and multiply top and bottom of this by 4, so that the denominators are the same. Cool. Now we're going to do 1 minus 4, that's negative 3. So the mechanical energy initial is negative 3 big G, big M, little m, over 4r. So negative 3/4 this. Okay. Now, they want to know the greatest distance from the center of the planet. So they want to know about the final mechanical energy. So keep this in mind, because we know that this is also equal to the final mechanical energy, which would also be equal to the object's potential energy out here. It has no kinetic, just potential. So it's just this. That, now, they want the distance from the center of the planet. So we're going to go negative G, big M, little m, over, I'm going to call this R, we'll call it max. This will include, when we figure it out, this will include the center of the planet. Okay. So this is equal to this stuff. And what we need to figure out is what this is. So let's give it a shot. So negative 3 big G, big M, little m, over 4r equals negative big G, big M, little m over r max. So some things happen here. Negatives are going to go away. G's and M's are all going to go away. So I really have 3/4 R. Look at it like that. No, not 3/4 R. That R is in the bottom. Be careful, Will. Be careful. Let's just keep it like it is. 3/4R equals 1/R max. Okay. The thing I want is in the bottom. I'm going to flip both of these. So I have, now I'm going to write it, 4/3 R, if I flip it, equals R max. So the maximum distance it goes is actually a factor of the radius of the planet. Interestingly enough, I get 4/3 R. That is D. My sources tell me number 13 is in fact D. I'm correct. All right, there was a lot of that. Hopefully you learned something. Let's move on to 14. All right. Pendulum has a length L and a bob mass of M. Which of the following is true of the linear momentum of the bob? Okay, so we haven't talked about momentum yet. Unless you caught, there was an earlier problem where I mentioned it. So this problem would understandably be a bit of a challenge, but all you need to know is momentum, two things about it, is simply mass times velocity. Faster an object goes, the bigger its momentum. And it's also, this is important, a vector. It has direction. So changing the momentum could be just changing the direction. Something going in circular motion has a constantly changing momentum, not because it's going faster or slower, but because it's turning. But momentum is a vector, unlike kinetic energy, which is not a vector, it's a scalar. So, as the pendulum goes from here to here, it picks up speed, yes? Goes, let me make sure it goes from the highest to lowest point. So yeah, it picks up speed. So the magnitude of the momentum should increase. V gets bigger. What about the direction? Well, that's always changing, isn't it? It's kind of moving in a circular path there. At least it's not kind of. It is moving in a part of a circular arc. So I'm looking for an answer that tells me that the magnitude goes up, but the direction changes. Let's see if there's one like that. It does not remain constant. It's conserved for a system, but this is an individual object. The external force would be gravity. It increases in magnitude and changes direction. I kind of like that one. It decreases in magnitude. No. It's not going slower. It's converted to angular momentum. Okay, we haven't even talked about angular momentum. Converted linear. No. It's converted into kinetic energy. Converted momentum into kinetic energy, that you don't convert from one to the other. They're different things. So this one seems to me to make the most sense. All right. 15. All right. 15 says, sled slides down a hill. Friction has friction. Okay. Between the sled and the hill, but negligible air resistance. Which of the following must be correct about the resulting change in energy of the sled Earth system? So we're including gravitational potential energy and kinetic here. All right. Well, if there's friction, some of its initial mechanical energy, this energy between the Earth and it, it's not going to have the same final, put it this way, if it goes from here to here as it goes down the hill, if there's friction, this and this are not the same. Some of this is lost, so to speak, to heat through friction. So I would expect there to be a decrease in the total energy between the Earth sled system. Because if there's no friction, it stays the same. If there is friction, it's got to be less at the end here. So the gravitational potential energy decreases, that's for sure. Kinetic energy does increase. The total energy decreases because you lose some to friction. So let's see if we can find, those are all the things I know would be true. The sum of the kinetic energy and the gravitational potential energy changes by an amount equal to the energy dissipated by friction. Yeah, I would buy that, right? Because that's the old mechanical energy initial plus the work done by non-conservative forces equals mechanical energy final. That would make sense. Let's see what this says. The gravitational potential decreases and the kinetic energy is constant. There's no way the kinetic energy is constant. If it starts at rest, it's moving down here. So no, because of that, no. The decrease in gravitational potential energy is equal to the increase in kinetic. That would only be true if there was no friction. Then that would be true. All the potential will be turned into kinetic. But not all of it is, because there's work done by a non-conservative force. So I gotta rule that out. Gravitational potential energy and the kinetic energy must both decrease. Definitely an increase in kinetic energy here. Alright? So, no. So yeah, it's gotta be A. It's always tricky when the correct answer is the first one. Moving on to 16. Looks like this. Student has to determine the work done on a block of wood when the block is pulled horizontally using an attached string. The student is supplied with a spring scale, a stopwatch, and a meter stick. Which of the following graphical analysis techniques will allow the student to determine the work done on the block by the string? Okay. So let's take a look at our answers. Spring scales. So spring scales are going to measure force, time for the stopwatch, and distance. If we want work done, I'm guessing distance is what we're looking for, and force, right? Force times distance. All right. So work, this is one of the key concepts for this whole bit. In a force versus distance graph, let's say you pull with a force that changes, it goes up with distance, the area under is the work done. So let's see if we can figure out something like that here. Graphing the force as a function of time and calculating the slope. I don't buy that. Graphing the force as a function of time. I'm going to get rid of both of those because maybe with momentum, later on we'll find out force times time is a thing. It's called impulse. But graphing the force as a function of distance and calculating the slope. Close, but I don't think we want the slope. Graphing the force as a function of distance and calculating the area under the curve. Bingo. That would do it. That would give us the work.